Welcome back. So I left you with a problem last time to calculate the flux in the V-band for a star with an apparent magnitude of 26, so quite a faint star. And the way to do that is to go to our relationship between ratios of fluxes and differences of magnitude. So going back to the real definition of magnitude system. So I'm going to use this version of the formula here, since we're interested in fluxes. And let's call star 2 Vega, which is the defined to be the zero magnitude star, basically. Okay, so if you do that, then you can see the zero is appearing here instead of M2. So M1 is the star that we're after the flux for. And now in here, instead of F2, we're substituting in the zero magnitude flux for Vega. That's what's going to go in there. And so if we just rearrange that formula, we get that the flux of the star we're interested in is the zero magnitude flux for Vega, just times this factor here, so 10 to the minus 0.4 times the magnitude of the star we're interested in. So this is quite a useful formula that astronomers would use a lot. Okay, so you look up the magnitude of a star, but what you actually want to do is find out the flux. So you first of all need to go and look at the zero magnitude flux in the particular filter that you're looking at. So in this case, it's the V filter. So this was the zero magnitude flux that I gave you last time. Here's the factor, and that just gives us the answer here of 1.5 times 10 to the minus 21. And the units here will be whatever units the original zero magnitude flux was in this case, watts per meter squared per nanometer. So again, it's not an SI unit, but a more convenient unit because nanometers are typically what we're using in the optical. Okay, so on to this week's, this lecture's topic. So we're, last couple of lectures really, we've been looking at what kind of information we can gain from the continuum spectra, okay, when we looked at the shape of the continuum light, but there's a huge amount more information encoded really in the spectra of stars rather than just the general shape of the continuum, and that comes in the form of absorption lines. Okay, so that's what we're going to look at in this lecture, are stellar absorption lines. So, what is it? What can they tell us? So we'll look into the sort of basic physics behind absorption lines first, and then we'll look at the temperature dependence of those. That's what really determines the strength of the lines in stellar spectra, different spectra of different stars, and that will lead us on to a classification system for stellar spectra. So a little bit of notation here, really. So as I promised last time, this is really going to lead us into a new way of determining the temperature for stars. Okay, so let's kick off by just showing you this picture. We had it in the introductory lecture, but this is a very detailed spectrum of our own sun, okay, going all the way from the sort of red wavelengths here, all the way through to the blue wavelengths down the bottom here. So you can think of this as little chunks of spectra, and to get the actual spectrum, you'd want to stack them all sort of side by side, which would obviously be an extremely long, a very long spectrum. So you can see that this here, the light coming in, the optical light, this is all optical light here, has been dispersed using a special prism to disperse the light so that you can see lots of examples of these little dark vertical absorption lines here. So these sort of patterns here, you can see there are strong ones, okay, but there are also very weak lines here. Okay, you can just see faint ones as well. And if you actually zoomed in even further and took a really deep exposure, you would literally find millions upon millions of these lines here. So, you can see how many there are down here. It's getting very dense. So this is the these absorption lines are what we kind of want to sort of use and decode. There's a huge amount of information in here. Later on in the module, we'll talk about the fact that they're used to sort of decompose the composition of the atmospheres of stars. This is how we know what stars are made of. You can think of this, it's a bit like a DNA fingerprint, really. It's telling you what the atmosphere of a star is made of. But before you can get to that sort of stage of interpreting it, you need to understand more about the sort of temperature dependence first. So that's what we're talking about today. Okay, so first of all, let's set up the conditions that give rise to a spectral absorption line. So there's kind of two components to this. You need a particular sort of geometry, and you need a difference in temperature. And what you basically need is a source of hot continuum radiation in the background, okay? And then in front of that, you need a layer of cooler gas, and that's where the absorption lines will be formed, okay? So we discussed when we were talking about the sun, and in particular the photosphere of the sun, and it's the photosphere where these absorption lines arise from. So you'll recall that the sort of temperature was dropping steadily with height in the photosphere as we go up through the atmosphere of the star. And so that sort of structure, if you like, so you've got a denser, hotter background deeper in the photosphere, okay? And then, of course, from our viewpoint, we're looking down through the atmosphere towards that deeper, denser, hotter layer. So the continuum light from stars is formed in that sort of denser, hotter layer. So in the sun, that would be where the where the temperature reaches 5,800 Kelvin. But superimposed on that is less dense, cooler gas. Okay? So 4,000, 5,000 Kelvin, that kind of gas. So that is in front of that hotter background. Okay. So the next diagram attempts to illustrate this. Ignore the sort of bottom half of this diagram. We'll come back to this later in the module. What we're interested in is the absorption line spectrum over here on the right. And so the idea, again, this is a pictorial version of what I just said in words. Okay, so imagine you've got some hot, basically like a black body. Okay, so here, just illustrated by a sort of traditional tungsten wire light bulb. Okay, so that's just a hot piece of metal. That would give you a black body spectrum. So if you looked at that through a prism, you would just get the continuum spectrum and nothing else. Okay, described by the Planck function. But if you stick a cloud of cold gas, cooler gas in front of it, so it just has to be cooler than this, as photons stream through here, they will get absorbed by particular atoms or ions or even molecules that are in make up this cloud of gas. Okay, so photons of particular wavelength will come in. If they're exactly the right wavelength, that corresponds to an energy level in one of the species in here, then that photon might get absorbed, and that photon will then be destroyed. And the energy from that photon goes into exciting an electron from a lower level up to a higher level in the atom in that cloud of gas. Okay. And because the photon has been destroyed, then you see a gap at that particular wavelength or frequency, which corresponds to that particular energy difference in the energy levels. Okay, so that's the idea behind forming an absorption spectrum, absorption line spectrum. So let's put a few words on those pictures that I've just been talking about. So in the spectrum of stars, I showed you the example of the sun. there really are a vast number of absorption lines from lots of different species. Okay. So the term species here I'm using to represent both atoms of all the different elements, okay, but then you've got all the different ionization states potentially of all the different elements as well. So you might have different states of ionization, okay? So with different degrees, different numbers of electrons missing from various elements. And of course, every time you ionize something, you remove an electron, that changes the entire energy level structure of that particular ion. And so that gives rise to a whole different load of wavelengths. Okay. Obviously, every different element of every atom of every element has a different set of lines. And in cool stars, you can actually end up forming molecules as well, sometimes quite peculiar ones, but you can have molecules as well. And they have another different energy level structure with a whole different set of lines as well. Okay. So species here stands for molecules, atoms, and ions of all the different elements. So you can begin to see why there are millions upon millions of different absorption lines. But we're not going to get bogged down in any complexity. I'm going to use the simplest one we can possibly use to illustrate how sort of stellar spectra work and how they allow us to probe the temperature of a star. And we're just going to use, again, the simplest element, hydrogen, which of course is also the most abundant. And we're going to discuss a particular series of lines due to atomic hydrogen, which arise, which are in the optical part of the spectrum. Now, historically, astronomy started out in the optical, of course, and of course most stars emit most of their radiation in the optical, so it's an obvious place to do that as well. Okay. I'm going to introduce a little bit of notation here. So atomic hydrogen, the way to read this is it's H1, so this is a Roman numeral 1. It doesn't look like it in this font, but that's a H1, so that's a Roman numeral 1. Okay. And this is where the kind of notation that spectroscopists used. So atomic hydrogen would be referred to as H1 when you're looking at their spectra. Okay, and that's sort of atomic hydrogen or neutral hydrogen. We'll come across a few more examples in a moment. Okay, so the Balmer series of lines in hydrogen arises from the second atomic level in the hydrogen atom. Okay, we'll show you an energy level diagram in a moment. Okay. But here's just a sort of schematic example, I'm going to show a few of these during this lecture. So this is a bit like a traditional old style photographic spectrum, where you would, put your starlight down the slit of a spectrometer and spread the light out into all its different wavelengths. But in essence, this is in the direction of the slit of the spectrometer. So you get a little vertical bit of spectrum where the starlight was landing through the slit. Okay. So that's why they look like this. Okay. We'll see some graphical displays later, but this is still true on modern detectors. If you look at electronic detectors, you still get an image like this as well. So just to orientate ourselves a little bit, so the Balmer series of lines has its strongest line here called H alpha. Okay, hopefully you can see that. So that is H alpha, the H alpha line, which appears at around 656 nanometers at the red end of the spectrum. And then the next line in the series is H beta. So they're given these Greek names to start with for the stronger ones. So that's H beta, and then we've got gamma, delta. You can see them getting closer and closer together as we go up here into the blue end, off the blue end of the optical spectrum. Okay. So we'll see where that pattern comes from in a moment. In fact, we'll see it right now. Okay. So this is what I would call an energy level diagram for the hydrogen atom. Okay. So obviously hydrogen's the simplest one we can look at. So you've just got a single electron orbiting around a proton. But as I'm sure you learned from A-level physics, quantum theory tells us that the electron can't just orbit around any old way. It can only orbit at particular distances from the proton, and those have to obey the quantum mechanical rules, and that basically ends up with this kind of energy level diagram where you've just got discrete energy levels which are labeled by this quantum number here, n. Okay, so that's the electronic quantum number. So n equals 1 is the lowest energy, or the ground state, as it's often called. And in terms of energy, we've got a little scale on here. So the ground state is 13.6 electron volts, so that's a unit of energy, below zero. So we're using putting the zero level up here for, it's a bit like electric potential energy, basically. Okay, and the next one up is the n equals 2 that we're interested in here. Okay, so if an electron is sitting in the n equals 2 level and a photon with the right amount of energy comes along, so with this energy difference here, it will be absorbed, and the electron will jump from n equals 2 to n equals 3, and that would give rise to this particular transition, which is the H alpha transition. So you would see a dip in here because all of the photons corresponding to this energy difference, and obviously, energy difference here, the energy of a photon is is equal to Planck's constant times the frequency, or hc over lambda if you're using wavelengths. So that that energy difference corresponds to a particular wavelength, and that would be the H alpha wavelength. If it jumped up from n equals 2 to n equals 4, then that would be the H beta line. Okay, and you can see that that takes a bit more energy, so therefore that is a bit of a shorter wavelength. So instead of H alpha being in the red end of the optical spectrum, you've got H beta in the blue end of the optical spectrum. As you go up the series, you can see that the gaps between the energy levels get smaller and smaller and smaller. Therefore, the series of lines gets closer and closer together. So when you look at this pattern of lines here, you're basically looking straight into the quantum structure of the hydrogen atom, okay? Which is why spectroscopy is so powerful in probing atomic physics. Okay? So this is the Balmer series here, okay? And we'll come back to this a few times in the module and this diagram a few times. So that process of going from a lower energy level to a high energy level is called absorption, okay? Because you're absorbing the photon. Okay, so just something to lead us into the next part. So we want to try and start relating this to sort of temperature a little bit. So you can see in that diagram that if an electron is sitting in the n equals 2 level of hydrogen, it needs another 3.4 electron volts of energy to become ionized, i.e. to become free, to be liberated from its proton and just become a free electron. So that process where you remove an electron from an atom by giving it energy is called ionization. So little exercise here for you to do during the break is to work out what temperature black body, okay, we had this in a previous lecture, okay, Wien's displacement law, what temperature black body would give a peak of its emission at the wavelength corresponding to an energy of 3.4 eV. Okay. Now, the electron volt is not an SI unit of energy, but it is very commonly used in sort of that energy level structure of atoms. So I mentioned verbally just now, the idea that the energy of a photon is h times nu, as I would normally call it. So using nu for frequency, you might have used hf in the past, but Planck's constant times the frequency. Okay. So, but we're not after frequency, we're after wavelength. Okay, so hopefully you can put all that together. Okay, so you can see the idea here. N equals 2, if an electron is sitting here, if we want to ionize an atom that is already sitting in the N equals 2 state, then we need to put in at least 3.4 electron volts of energy in order to get the electron from here all the way out up here. So N equals infinity here corresponds to effectively when the electron becomes free. So you can give it more energy, but you need at least this amount in order to remove it from the atom, so that you would then have a free electron and just leave the bare proton behind. Okay, so I'll leave you with that little task. Have a go at in the break.